Good morning. Myself Chandana. I am from CSC department. Today I want to tell about 4queen problems. Let's enter into the topics. Topics of introduction, how to solve the 4queen problem, approach to solve the 4queen problem, solution to solve 4queen problem using space tree, algorithm for n-queen problem, complexity, advantages of using backtracking, and last conclusion. Let's enter into the topics. First one, introduction. The 4queen problem is a puzzle that asks how to place 4 queens on a 4x4 chessboard such that no two queens threaten each other. Queens can attack other pieces along the rows, column, and diagonals. Therefore, the challenge is to ensure that no two queens share the same row, column, or diagonal. This is a specific case of the more general n-queen problem where the objective is to place n-queen on an n into n chessboard under the same constraints. Our challenge is no two queens should be in same column, same row and diagonal. Then only the queens can be satisfies the condition. Next, how to solve the 4queen problems. Before entering into this topic, actually this problem is based upon the backtracking, so that we have to know what is meant by backtracking. Backtracking is a technique where we explore all possible solutions by incrementally adding the solution and backtracking wherever we find that the current solution is invalid. For example, if you take 4 queens in a chessboard, first we place q1 in a first row and first column, then again now place q2. What are the chances to place q2? Second column, third column and fourth column. But if you place q2 in the second column, 1 2 will be in the diagonal, so we should not place q2 in the second column. So where we had to place q2? We had to place q2 in the third column. See, if you place q2 in the third column, we can't place q3 in the third row, because if you place q3 in the first column, already we placed q1 in the first column, so we can't place. If you place q3 in the second column, if you place q3 in the second column, we already placed q2 in the third column, and 3 and 2 will be in the diagonal, so we can't place q3 there. If you place q3 in the third column, 2 is also placed in the third column, so we won't place q3. If you place q3 in the fourth column, 2 and 4 will be in the diagonal, so we can't place q3. So now what we had to do? We had to do backtrack. Backtrack means nothing but if we won't get any solution, we want to change that the queen to the next row. Now we can change q2 to the fourth row. Then we can get q3 to place. So that is known as backtracking. Here, step-by-step explanation of backtracking approach to solve the 4queen problem. Start in the first row and try placing a queen in each column one by one. Check for conflicts. After placing a queen, check if it is safe. A position is safe if no other queen can attack it. No other queens in the same column. No other queens in the same diagonal. When we are placing a queen, first we have to remember that no two queens should be in the same column, same row and the diagonal. If placing a queen leads to a solution, move to the next row and repeat to the process. If placing a queen leads to the conflict, backtrack, remove the queen and try the next column. If all columns are tried and no solution is found, backtrack to the previous row. Approach to solve the 4queen problem. In the 4queen problem, we aim to position for 4 queens q1, q2, q3, q4 on a 4x4 chessboard so that no two queens threaten each other. Let's consider the placements of the first queen. What is our approach? We had to place 4 queens in the chessboard. This is our approach. With that approach, we had to remember that condition. The condition is no two queens should be in the same column, same row and the diagonal. Let's consider the placement of the first queen q1 at position first row first column on the chessboard. However, this restricts the options for placing the second queen q2 since it cannot be placed in the same row as q1. See here, if we place if we place q1 here, if we place q1 here, now check for q2. Is there chance to place q2? No, we won't have any chance. Is there any chance to place q2 here? No, we won't have any chance. Is there any chance to place? Yes, we can place q2 here. If you place q2 here, now check where you had to place q3. Is there chance to place q3 here? No, there is no chance to place q3 here. Is there any chance to place q3? No. Is there any chance to place q3? No. Is there any chance to place q3? No. In first only we said if we won't get any solution, then what we had to do? Now we had to backtrack because we are not getting any solution to place q3 in the chessboard. So now what we had to do? Now we had to change the place of q2. Now we have to change the place of q2. See, now if you place q1 here, place q2 here, then what are the chances to place q3? In first column there is no chance to place q3. In second column we can place q3. Okay. Now we have to check for q4. If you place q4 in the first column, is this condition satisfied? No. If you place q4 in the second column, is the condition satisfied? No. If you place q4 in the third column, is condition satisfied? No. If you place q4 in the fourth column, is condition satisfied? No. So now what we had to do means, now we had to do again backtrack. Now we had to change the q1. Now we had to change q1 position. Now change q1 to the second column. So place q1 here. Now check again q2. Do we can place q2 here? No. Do we can place q2 here? No. Do we can place q2 here? No. Yes, we can place q2 in the fourth column. Is there any chance to place q3? Yes, we can place here and we can't place in this. Is there any chance to place q4? No. Is there any chance to place q4 here? No. Is there any chance to place q4 here? Yes. Is there any chance to place? No. So we got one solution. So like this we have to check for the solutions. Let's consider the placements of the first queen q1 at position 1, 1 on the chessboard. However, this restricts the options for placing the second queen q2. Now only we check like that one, since it cannot be placed in the same row as q1. After considering the available rows, we decide to place q2 at second row third column. However, this choice limits the possibilities for placing the third queen q3 as there are no available positions in row. In this solution, we need to backtrack to the previous step and reconsider the placements of q2. We move q2 to the position 2, 4 means second row fourth column, and now we find a suitable position for q3 at third row second column. However, these placements leaves no options for placing the fourth queen q4. Once again we backtrack to the placement of q1 and modify it to first row second column instead of first row first column. By making this adjustment, we can safely place q2 at second row fourth column, q3 at third row first column, and q4 at fourth row third column. Hence we obtain the solution 2 4 1 3, which represents the positions of the 4 queens on the chessboard. It is one possible solution for the 4 queen problem. To find alternate solution, we need to backtrack. Now we check q1 at the place first column, so we didn't get any solution, and again we checked q1 at the second column, so we got one solution. Next we had to check q1 at the third column. If you place q1 at the third column, we can get another solution. Another possible solution for the 4 queen problem is 3 1 4 2. Again check, if you place q1 at the fourth column, again we won't get any solution. So for 4x4 chessboard, we will get only two solutions. Solution to solve 4 queen problem using space tree. Totally we have 65 nodes for the 4x4 chessboard. See, first take one chessboard. Now consider the first queen. What are the chances to place first queen? So total 4 chances will be. We can place first queen 1 at the first column, queen 1 at the second column, queen 1 at the third column, queen 1 at the fourth column. If you place q1 at the first column, now check for q2. Is there chance to place q2 in the second row? Yes, we have two chances to place q2 in the second row. One chance is at the third column and another chance is at the fourth column. Now check for q3. If you place q2 at the third column, we won't get any solution to place q3. So now we had to backtrack, we had to go back and we had to check, is there any chance to place q2 at the fourth column? Is there any chance to get solution for q3 to place at the third row? Yes, we can place q3 at the second column, but we won't get any solution to place q4 at the fourth row. Now again go back. Now change the placement of the q1. Change the place of q1 to first row to first column to second column. Now check. Place q2 at the fourth column, q3 at the first column, q4 at the third column. So we got one solution. Now again do the same process for placing the q1 at the third column. When we place q1 at the third column, q2 will be placed at the first column, q3 will be placed at the fourth column, and then q4 will be placed at the second column. So we got another solution. Next, check the another condition. When we place q4 at the fourth column, when we place q4 at the fourth column, we have two chances to place q2 at the second column. One is we can place q2 at the first column and we can place q2 at the second column. If you place q2 at the first column, we can get to place q3 at the third column, but we won't get to place q4 in the fourth row. If you place q2 at the second column, we won't get chance to place q3, so we had to stop there. So only two solutions we can get on 4x4 chessboard. Here step-by-step logic for the generating the state space tree. Begin by considering each position in the current row. Check all the previous row to determine if there is already a queen placed in any of the column. Additionally, check the previous diagonal columns to verify if there is a queen placed in any of these positions. If either of these condition is true, indicating that two queens would be attack each other, backtrack to the previous row and move the previous queen one step forward. If none of the previous position conflict, place the current queen in the current position to move the next row. For this also, we had to check the condition, that is, no two queens should be in the same column, same row on the diagonal. Let's go to the algorithm for n queens problem. Place k of I for j 1 to k minus 1 if x of j is equals to our absolute x of j minus I is equals to absolute j minus k, return true. N queen of k comma n for I 1 to n do. If place k comma I, then x of k to I. If k equal to n, then write x of 1 to n. Else n queens k plus 1 comma n. Complexity. Time complexity of n queen algorithm for finding the single solution where the first queen q has been assigned the first column and can be put on n position. The second queen has been assigned the second column and would choose from n minus 1 possible solution, and so on. The time complexity is big O of n into n minus 1 into n minus 2 into and so on 1. That is, the worst case time complexity of n queen problem is big O of n factorial. This is not only for n queen problem, this is for 4 queen problem and the 8 queen problem. This, for finding all the solutions to the n queens problem, the time complexity runs in the polynomial time. Advantages of using backtracking. Ability to find the count all the possible solutions rather than just one. Parallel version of algorithm can increase speed several times. Conclusion. In conclusion, the 4 queen problem involves placing 4 queens on a 4x4 chessboard without them threatening each other. By using backtracking, we can systematically explore all possible solutions. This approach can be extended to solve the n queen problem. By understanding the concepts and implementing the provided code, we can efficiently find valid queen placements. The 4 queen problem serves as a stepping stone to tracking larger instance and exploring combination optimization. Thank you.